If you're lying here right now with even a faint anxiety about the words differential equation, maybe you took a class once and it didn't go well. Maybe you only know the phrase by reputation. Maybe something in your chest tightened. Just hearing the name. I want to say something simple before we do anything else. You're fine. Whatever happened before, whatever that subject made you feel, none of that matters tonight. Because here's the honest truth about what a differential equation is. Not the textbook version with the Greek letters and the little subscript symbols and the notation that seems designed to make you feel excluded. The actual idea, a differential equation, is a sentence. That's it. A sentence that says, this thing is changing. And here's the rule that governs how fast it changes, not the value of the thing at any given moment. Just the rule, the relationship between a quantity and its own rate of change. Think of it this way. Imagine I hand you a recipe card that doesn't say, set the oven to 350 degrees. Instead, it says, the hotter the oven, the faster the cake rises. That's not a number. It's a relationship. It connects one quantity temperature to the rate at which another quantity height is changing. That rule, that sentence about a relationship between a thing and how it's changing, that is, at its heart, what a differential equation is. And once that clicks, this subject starts to feel like something different entirely. It stops feeling like a wall built to keep people out. It starts feeling like a very old question, one that humans have been stumbling toward for thousands of years, long before anyone had the language to write it down. That's the story we're following tonight, the whole arc of it from the beginning. So wherever you are, settle in, let your shoulders drop. We're going to go through the entire history of differential equations, where they came from, what they mean, what they describe, and how they became the language underneath almost everything in the modern world. Nice and slow, no rush. There is nowhere else to be. Now, let's go back a very long way. I want you to picture ancient Babylon, not the ruins, but the city at its height somewhere between 1800 and 400 years before the Common Era, which puts us 3.5 to nearly 4,000 years ago. This is a city with ziggurat temples and canal networks and scribal schools where mathematics was a serious, respected profession. Babylonian mathematicians kept detailed records on clay tablets pressed with a reed stylus. They computed interest on loans. They developed methods for solving what we'd now recognize as quadratic equations more than 1,000 years before anyone in Europe had the concept of algebra. And some of those mathematicians spent their nights watching the sky. Picture this. You're a Babylonian astronomer. Your actual job, the thing your society pays you to do, is to track Jupiter as it moves across the heavens. Night after night, you observe and record. Where was Jupiter last night? Where is it tonight? How far has it moved? After weeks of careful observation, you notice something. Jupiter doesn't move at a constant rate. Some nights it covers more sky, some nights less. There's a rhythm to it, an acceleration and a deceleration, as if the planet is breathing in and out. You don't have algebra, No coordinate system, no concept of a function, no graph. You have a reed stylus and wet clay. So here's what you do. You draw a trapezoid on the tablet, a four-sided shape, two parallel sides, two slanted ones. The two parallel sides represent Jupiter's speed at the start of a time interval and its speed at the end. And the area of that trapezoid, that area represents the total distance Jupiter has traveled. Just sit with that image for a moment. A Babylonian astronomer pressing shapes into wet clay by lamplight, computing the area under a velocity curve to find a planet's total displacement, using a geometric method that is, in its logical structure, identical to what calculus students do today. And we know this because we have the tablets, actual physical clay tablets, surviving to the present, written in cuneiform script. In 2014, a historian of mathematics named Mathieu Ossendriver published a careful analysis of a set of Babylonian astronomical records and demonstrated that astronomers in ancient Mesopotamia were using exactly this trapezoidal method to track Jupiter's motion. Some of the tablets date to around 300 years before the Common Era, though the methods themselves are likely far older. When I first read about this, there was a moment where the sheer distance of it just landed. The Roman Empire hadn't been founded, the Parthenon hadn't been built, and someone was already performing the core computation of integral calculus on clay. What they were doing has a name now: integration. The accumulation of many tiny quantities, in this case, many tiny slices of velocity to find a total. It's one of the two central operations of calculus, and the Babylonians were doing it with nothing but geometry and patience. To track a point of light in the night sky, they weren't writing differential equations. They were solving a specific problem with a specific clever technique. But the question buried inside that technique, how do I work with something that is changing at a changing rate? That question is the seed of everything in this series. Let's move slightly. Egypt, around 1700 years before the Common Era. There's a document called the Moscow Mathematical Papyrus, written by an Egyptian scribe approximately 3,700 years ago, containing a formula for the volume of a truncated pyramid, a frustum, which is basically a pyramid with the top sliced off. And the formula the Egyptians wrote down is correct, not approximately correct, exactly right. To derive that formula properly using the tools we'd normally use today, you need integral calculus. And yet there it is, on papyrus, almost 4 millennia ago. How did they get it? We honestly don't know. The papyrus doesn't explain the derivation, it just states the procedure. Whether the derivation was once understood and has been lost, or whether it was arrived at by some geometric argument we haven't reconstructed, we can't say for certain. What we can say is that someone thought very carefully about how the cross-sectional area of a pyramid changes as you move up through it. That's a problem about how a quantity changes as another quantity changes. It's a differential idea, even if no one called it that. Let's jump forward a few centuries to a figure who came tantalizingly close to something that wouldn't fully arrive for almost 2,000 years. Archimedes, born around 287 years before the Common Era, in the city of Syracuse on the island of Sicily, one of the great Greek-speaking cities of the Mediterranean world. Archimedes is famous for many things, but what interests us is something specific. He was working on spirals, the Archimedean spiral. Picture a coil spiraling outward from a center point, each loop maintaining a constant distance from the previous one, like the groove on a vinyl record. Archimedes described it precisely. It's the path traced by a point that is both moving along a line at constant speed and rotating around a fixed center at constant speed. And Archimedes wanted to know at any given point on this spiral, what direction is the curve heading? In geometric language, he wanted the tangent line, the line that just grazes the curve at one point, pointing in the exact direction the curve is traveling at that instant, not an average direction across an interval, the instantaneous direction at a single point. Now here's what I want you to notice about that question. What Archimedes was asking in geometric form is, how is this curve changing right now at this specific instant? That is a derivative, not in the formal algebraic sense. Archimedes had no algebra. But the question is structurally identical to the question the derivative was invented to answer. He had to reason through it geometrically, case by case, constructing approximations that got closer and closer without quite arriving. And he got the right answer. He found the tangent to his spiral. Archimedes died in 212 before the Common Era, during the Roman siege of Syracuse, reportedly stabbed by a soldier while he was working on a geometry problem in the sand. Apparently unconcerned enough about the Roman army to finish his calculation first, he never knew that the question he'd been circling would eventually become the foundation of a revolution in human understanding. He was just following the problem because the problem was interesting. Now let's move east and considerably forward in time. India, late 6th century of the Common Era. A mathematician named Brahmagupta was born in 598 CE in what is now the Rajasthan region of northwestern India. Brahmagupta is one of the most important figures in the history of mathematics, the person who gave the first formal, systematic treatment of zero as a proper number with consistent arithmetic rules, not just an absence or a placeholder. He worked on quadratic equations, on the geometry of cyclic quadrilaterals, and on problems of motion. When Brahmagupta wrote about objects moving at changing speeds, about how to find a position after some interval of time, given a rule about how speed was changing, he was asking questions that live in the same conceptual territory as differential equations. He didn't have the algebraic machinery to write them that way, but the problems required him to think about rates of change, about the relationship between speed and distance in a world where those quantities don't stay still. And then, a few centuries later and a few thousand miles to the west, a man was doing something remarkable with light. Ibn al-Haytham, born around 965 CE in Basra, in what is now southern Iraq, and doing much of his most important work in Cairo. His major work on optics, the Kitab al-Manazir, was read and cited by European scientists for 500 years after his death. He was obsessed with how light moves, how it reflects, how it bends when crossing from air into water, the geometry of refraction and surfaces with varying curvature. Some of the problems Ibn al-Haytham worked on involved what we'd now call optimization, finding the point or path that satisfies some extremal condition, some minimum or maximum. These are fundamentally differential problems. The question underneath them is always a version of where does this quantity stop increasing and start decreasing? Where is the rate of change equal to zero? He was navigating this conceptual territory with great sophistication, building on Archimedes and extending far beyond him, while working in a mathematical tradition that European scholars would not have access to for centuries. Here's the thing, and I want to say this carefully, because I think it's one of the most remarkable patterns in all of intellectual history. For something like 3,000 years, humans could feel differential equations. They could see them in the arc of a thrown rock, the way it slows as it rises. Px then falls faster and faster, the rate of height change shifting continuously throughout the motion. They could sense them in the cooling of hot metal, losing heat quickly at first, then more slowly as it approached the temperature of the surrounding air. The rate of cooling, depending on the current temperature difference, they could observe them in the orbits of planets, in the bending of light through a lens, in the draining of water from a vessel faster when the water is deep, slower as it shallows. These patterns were everywhere. Every craftsman, every sailor, every astronomer, every farmer working alongside a flooding river had encountered some version of this question in their work. This thing is changing, and the way it's changing seems to depend on the thing itself. What is the rule? And here's what's genuinely extraordinary about this. They could solve specific versions of it. The Babylonians had their trapezoidal method for planetary motion. Archimedes had his geometric argument for the spiral tangent. The Egyptian scribes knew the formula for their pyramid. Each one had a technique, hard one and specific, but none of them could write it down in general. None of them had a language for the idea in its universal form. Imagine trying to describe how a river flows to someone who has never heard the word speed. You could walk them to the bank and point at the water. You could throw in a leaf and watch it travel. You could describe the current going faster in the narrows and slower in the shallows. But without the abstract concept, without the word, you can never write a general rule. You can solve the river you're standing next to. You can't solve all rivers. That's what these mathematicians were facing for 3,000 years. The question showed up in problem after problem, in culture after culture, from clay tablets to papyrus scrolls, to the geometry of spirals, to the optics of light. But the language to capture it in its full generality, the symbolic machinery, the conceptual framework, the notation that could write any rule about change in a single sentence, that language didn't exist yet. The question existed, the language didn't, and that language, when it finally arrived, would come from two men who despised each other, working on opposite sides of Europe, solving the same problem, and igniting one of the bitterest feuds in the history of science. So the language arrived, and once it arrived, nobody could stop using it. In 1687, Isaac Newton published his Principia Mathematica, and in the same decade, Gottfried Wilhelm Leibniz published his own version of calculus from a different starting point, with different notation, and an almost completely different philosophical framing. The priority dispute between them became one of the ugliest academic feuds in history, and we'll set that aside for now. Because what matters for our story is what happened next. Because once the language existed, once you had a notation that could write the rate at which something changes as a single symbol, and then write rules about that symbol, and solve for unknown functions, mathematicians basically couldn't stop. It was like someone had handed an entire generation of brilliant people a musical instrument that could play chords nobody had ever heard before. They played everything. The first thing worth noticing is how quickly differential equations appeared in real physical problems. Almost immediately. Newton, yes, the same Newton who co-invented calculus, made one of the first explicit appearances of what we'd now call a differential equation in a completely everyday observation. He noticed something about hot objects cooling down. If you pour yourself a cup of tea and leave it on the counter, it cools quickly at first, when it's still very hot, and more slowly as it approaches room temperature. Newton formulated this as a precise mathematical statement. The rate at which the tea cools, he said, is proportional to the difference between the tea's temperature and the temperature of the room. That's it. That's Newton's law of cooling. If you write that statement in the language of differential equations, it becomes one of the cleanest equations you've ever seen. The solution is an exponential decay. Temperature starts high, falls fast, then slower and slower, approaching room temperature like a line it can never quite reach. The tea is always trying to reach equilibrium. It just gets infinitely closer and never quite arrives. Here's the thing worth sitting with for a moment. That single differential equation captures the behavior of every cooling object, everywhere. Under those conditions, a cup of tea, freshly poured, concrete hardening in winter air, a star contracting under its own gravity, the same equation, the same story about change. This is what Newton and Leibniz had unlocked. Not just a clever tool for one problem, but a language for stating laws, and from those laws, deriving exact predictions about how the world unfolds. Now, let's introduce a family in the city of Basel, in what is now Switzerland. In the late 1600s, there was a family named Bernoulli. Over 3 generations, this one family produced 8 significant mathematicians. 8. The father, Jacob, born in 1655. His younger brother, Johann, born in 1667. Johann's son, Daniel. Dat, born in 1700. And several more besides. The Bernoulli family's contribution to mathematics and physics is so large that when scientists today write equations involving fluid dynamics, probability, or the calculus of variations. They are almost certainly using something a Bernoulli discovered. Usually they're not entirely sure which one, but for all their brilliance, they were also kind of a disaster as a family. Let me tell you about the brachistochrone problem, because this is where the story really catches fire. It's 1696, Johann Bernoulli, 30 years old, brilliant and entirely aware of it, published a challenge in the leading mathematical journal of Europe. He called it the brachistochrone problem. The name comes from the Greek for shortest time. The question was this: imagine you have 2 points, one higher and one lower, and you want to connect them with a ramp. A ball starts at the top and rolls down under gravity. No friction. What shape of ramp gets the ball there in the shortest possible time? Your first instinct is probably a straight line, but that's not the answer. And this is one of those results you have to see before you believe it. Picture designing a water slide. If you want riders to reach the bottom fastest, you don't build a straight ramp at the constant slope. You build one that drops almost vertically at first. Ooh. So the rider picks up speed immediately, then flattens into a sweeping arc. The straight ramp keeps things slow and steady. The curve wins. The shape that wins by the largest margin is called a cycloid. The curve traced by a single point on the rim of a wheel rolling along a flat surface. Beautiful, specific, and not at all obvious until you solve the differential equation describing it. Johann sent this challenge to the mathematicians of Europe and gave them 6 months. 5 solutions came back. Jacob Bernoulli solved it. Leibniz solved it. A French mathematician named Guillaume de l'Hôpital solved it. And 2 solutions arrived without names attached. What anonymous solution, in particular, caught Johann's attention? No name, no identifying information, just the solution itself, perfect and complete. When Johann read it, he reportedly smiled. He knew exactly who had written it. I recognize the lion, he said. By his claw, the lion was Newton, who had received the problem at 4 in the afternoon, solved it overnight, and submitted it without any interest in being credited. Let that sit for a moment. Newton solved the brachistochrone problem before breakfast. He was 53 years old, had not been actively working in mathematics for years, was busy running the Royal Mint, and he just dashed it off. Anonymous, no fanfare. I find this story almost unreasonably satisfying, partly because of what it says about Newton's almost inhuman mathematical ability, even in later life, and partly because of what it says about Johann Bernoulli, that a man could read an unsigned solution and recognize the mind behind it. The particular style of a mathematical argument, its elegance, its specific choices, was as distinctive as a signature. Mathematics has fingerprints. Johann could read them. Not long after, another differential equation entered the picture. The catenary problem. You've seen a catenary without knowing its name. Hang a heavy chain between 2 posts. That graceful, drooping arc it makes is called a catenary. For centuries, mathematicians assumed it was a parabola, Same general shape, easy to confuse. Galileo thought it was a parabola. He was wrong. The actual shape requires solving a differential equation involving the hyperbolic cosine function, which had barely been formalized at the time. When the correct answer came, it came from three people more or less simultaneously: Leibniz, Christian Huygens, and Johann Bernoulli himself, all working independently, all arriving at the same strange, elegant curve. The catenary turns up everywhere once you know to look. Suspension bridges, power lines, the gateway arch in St. Louis, which is an inverted catenary, chosen because that shape distributes the arch's weight perfectly, with no bending stress anywhere in the structure. None of that engineering knowledge exists without differential equations. But here's where this era shows its darker face. Johann Bernoulli had a son named Daniel, born in 1700, raised in Basel, trained partly by his father. Daniel was possibly the most gifted of all the Bernoullis, with a kind of intuitive lightness in his thinking that even his formidable father had to acknowledge. Daniel took a position at the St. Reblev, Petersburg Academy of Sciences, spent roughly 8 years in Russia, and what he produced there changed the course of physics. In 1738, Daniel published a book called Hydrodynamica. It was a masterpiece. It contained what we now call Bernoulli's principle: the faster a fluid moves, the lower its pressure. That single insight explains why airplane wings generate lift, why a curveball curves, why a perfume atomizer pulls liquid up into the stream of air. The Paris Academy of Sciences awarded the book a prize, and here is the part that makes me feel a little sick every time I come back to it. Johann Bernoulli, Daniel's father, was furious, not because the book was wrong, because it was too good, because it had won a prize that Johann had also entered, and Johann had lost to his own son. So Johann sat down and wrote his own book on fluid mechanics. He called it Hydraulica, and then, quietly, he backdated it. He claimed it had been written in 1732, 6 years before Daniel's Hydrodynamica. He presented it to the mathematical community as evidence that the ideas in Daniel's book were not Daniel's discoveries at all. They had been his, Johann's, all along, a father claiming credit for his son's work, backdating a scientific paper, trying to rob his own child of the discovery that would define his career. Over a differential equation, Johann went further. He refused to acknowledge Daniel's work publicly. He lobbied against Daniel receiving recognition. By several accounts, he eventually banned Daniel from his house entirely. Their relationship, already strained by years of competition, where a father should have been a protector and a mentor, never recovered. Daniel outlived his father by 34 years and reportedly never spoke warmly of him. The mathematical community saw through it. The dates were inconsistent. Johann's reputation for this kind of rivalry was already well established. Nobody was truly fooled, but the damage to Daniel was real, and the act itself was what it was. A man who could solve differential equations in his sleep, choosing to use that intelligence as a weapon against the person he should have protected most. Just think about that for a second. Of all the things Johann Bernoulli is remembered for, one of the most lasting is this. Now, enter Euler. Leonhard Euler was born in Basel in 9707, just a few streets away from the Bernoulli household, son of a Protestant minister, a methodical and unusually quiet child who showed an extraordinary gift for mathematics before he was a teenager. He enrolled at the University of Basel at 13, master's degree at 17, writing a thesis comparing the philosophical systems of Newton and Descartes. He applied for a professorship in physics in Basel at 19, didn't get it, and went instead to St. Petersburg, where Daniel Bernoulli had recently been working. He arrived at 20. He would go on to become, by essentially any measure, the most productive mathematician in the history of the subject. Here's the human detail that I think matters most in Euler's story. When he was 28, Euler lost the sight in his right eye. The cause is uncertain. Some accounts say he damaged it solving in 3 days, a problem that others had estimated would take months. Others blame an illness. By his early 30s, the eye was functionally gone. By his late 50s, a cataract had taken the sight in his left eye as well. By his mid-60s, Leonhard Euler was almost completely blind. He did not slow down. He had trained himself to perform entire calculations in his head. He could hold a system of equations in his mental workspace, manipulate it, derive new conclusions, and dictate the result without writing down a single intermediate step. After a fire in 1771 destroyed his house and many of his papers, Euler dictated roughly 500 papers in the following decade. 500 papers, 10 years, no eyes. There's something deeply satisfying about the contrast here. While Johann was backdating papers and banning his son from dinner, Euler was writing textbooks because he thought students deserved clearer explanations than what existed. He named results after other people. He credited sources freely. He corresponded generously with every mathematician in Europe, sharing ideas he could easily have published first himself, treating the growth of mathematics as a communal project rather than a competition. The Bernoulli bitterness and the Euler generosity existed at exactly the same moment, in exactly the same field, among people who knew each other well. The contrast is not subtle, and what Euler did for differential equations was nothing less than building a road system through a jungle. Before him, you had scattered individual solutions. Newton's cooling law here, the brachistochrone curve there, the catenary somewhere else. Each one a brilliant feat arrived at by its own specific clever argument. Every new differential equation required a new burst of ingenuity. There were no general methods, no shared framework. Euler built the roads. He noticed that the exponential function e raised to the power of x had a remarkable property. Its derivative, the rate at which it changes, is exactly itself differentiated, and you get the same function back, which means it is the natural solution to the simplest possible differential equation, the one that says simply that the rate of change of something equals the thing itself. That equation governs population growth, radioactive decay, compound interest, the charge draining from a capacitor through a circuit. One equation, one solution, dozens of different physical stories, all written in the same grammar. Euler used this as a master key. He showed that by taking the exponential function and modifying it, combining it with complex numbers, using it as a building block, you could construct solutions to enormous families of differential equations that had previously seemed unrelated. He developed a method of integrating factors, which converts a difficult equation into something solvable by a standard procedure. He built systematic methods for second-order equations, the ones governing oscillation and wave motion, and every vibrating string in existence. He began to see differential equations not as isolated puzzles, but as a landscape with underlying structure, where once you understood the lay of the land, whole families of solutions became visible at once. And here's what makes this era so remarkable. Within about 60 years of calculus being invented, differential equations had gone from a thing that exists to the primary language in which every law of physics would be written. Every single one. Newton's laws of motion are differential equations. The laws of electricity and magnetism that Maxwell would write down in the 1860s are differential equations. Heat flow, fluid motion, elastic vibration, wave propagation, all differential equations, all running on the framework that Euler built and organized and made navigable for everyone who came after. Before we move forward, there's a thread worth acknowledging, because this story belongs to more than Europe. The Arabic algebraic tradition, which gave the word algebra to every language that uses it, had been developing symbolic reasoning about quantities and relationships for centuries before Newton. Ibn al-Haytham, working in Cairo and Basra around the year 1000, reasoned about optics and light using ideas about rates of change that prefigured the differential approach. The Kerala mathematicians of southern India, working in the 14th and 15th centuries, developed infinite series and computational methods that fed directly into the tools Leibniz and Euler would systematize. Arabic algebra, Persian astronomy, Indian trigonometry. These were not footnotes to the European story. They were the ground it was built on. The language was real now. The tools were in hand. The roads were open. But there was a problem nobody had solved yet. What happens when you heat one end of a metal bar and let the heat spread through the whole thing? Not a single object cooling uniformly like Newton's tea, but an entire field of temperature, changing at every point along the bar, at every moment in time. The answer to that question would come from a man with no formal mathematics training, who worked as an engineer and a politician, and whose solution would split the entire mathematical establishment in half. His name was Joseph Fourier. He was born in 1768 Zoll Auxerre, a small town in central France, the ninth child of a tailor who died before Joseph turned 10. He was raised by monks, educated in a Benedictine monastery, and then somehow pulled into one of the most frightening episodes in European history, During the Revolution, Fourier got swept up in local politics because in the early 1790s in France, if you were young and educated and even slightly idealistic, the revolution pulled you in like a tide. For a while, this was fine. And then the terror arrived. Fourier was arrested in 1794, accused of insufficient revolutionary fervor, which was essentially a death sentence with political language wrapped around it. He was imprisoned. He fully expected to die. He didn't. Robespierre fell before Fourier's turn came, and he walked out of prison into a France that was reorganizing itself around a 30-year-old general named Napoleon Bonaparte. Napoleon noticed Fourier. He brought him on the Egyptian expedition of 1798, that remarkable campaign where Napoleon traveled not just with an army, but with an entire team of scholars and scientists, briefly occupying a civilization and trying to document it at the same time. Fourier spent years in Egypt, helped produce the great scholarly survey of Egyptian culture, then came back and became a prefect, an administrator, a reasonably competent cog in the Napoleonic machine. And then, in the quiet spaces between governing and administering, he worked obsessively on heat. Here's the problem he was trying to solve. Picture a long, thin metal rod. You heat one end of it. The heat spreads along the rod over time. Gradually and unevenly, the temperature changing at every point and every moment. Each region influenced by the regions immediately beside it. Newton had given us the equation for how a single object at a uniform temperature cools toward its surroundings. But this was different. This was an entire field of temperatures, an infinite collection of values, one at each location along the rod, all shifting through time, all pulling on each other. The question was whether you could write one equation that captured all of that. At every point, at every instant, simultaneously, Fourier wrote the equation. What he produced is called the heat equation, and it's a partial differential equation, an equation that describes how something changes across both space and time at once. In plain terms, it says that the rate at which temperature changes over time at any given point depends on how steeply temperature is curving through space around that point. Cold, surrounded by hot, warms up quickly. Hot, surrounded by cold, cools down quickly. The equation describes that interplay precisely, everywhere along the rod, at every moment. That was brilliant. But Fourier's second claim is the one that split the mathematical establishment in half. To solve the heat equation, to find the actual temperature at any specific point in time, you need to specify a starting condition. What does the temperature distribution along the rod look like at the very beginning? And Fourier's proposal was this: any starting distribution, no matter what shape it has, can be expressed as a sum of sine and cosine waves added together. I want to dwell on this for a moment, because this is one of those ideas that sounds simple until you really let it in. Sine and cosine waves are the most peaceful, most well-behaved curves in mathematics. They oscillate gently, rising and falling in perfect, smooth cycles. no edges, no corners, no surprise. A sine wave is what pure sound looks like, a single pitch, vibrating at a steady frequency, going on forever. Fourier's idea is like saying every sound you've ever heard, a violin, a thunderclap, a human voice, a crowded street corner, is secretly just a combination of pure, boring whistles at different pitches and volumes. Take enough whistles and you can build any sound. Take enough sine waves and you can build any shape. And Fourier was saying, take any temperature distribution you like. Make it as strange and angular as you want. Make it a sharp spike, the temperature extremely high at exactly one point and zero everywhere else. Make it a perfect square wave, hot on the left half of the rod and cold on the right, with a hard vertical drop at the boundary. A discontinuous jump from one value to another with no transition at all. Make it the most irregular, jagged, unpredictable profile you can imagine. Fourier's claim was that you could build that profile by adding sine and cosine waves together, not approximately, exactly. Stack enough of them, infinitely many if necessary, at higher and higher frequencies, with smaller and smaller contributions, and they combine into precisely the shape you specified. The hard corner of a square wave isn't a different kind of mathematical object from a smooth oscillation. It's what you get when infinitely many smooth oscillations at exactly the right frequencies and exactly the right amplitudes interfere with each other at the same location. The sharpness is emergent. It arises from the cooperation of things that are individually incapable of sharpness, which, I mean, think about what that implies. The spiky and the smooth are secretly built from the same material, the most violent, discontinuous shape you can draw, and the most gentle, a flowing wave, are not opposites. They are the same thing expressed at different scales of patience. I genuinely find this one of the most beautiful facts in all of mathematics. And I don't think that feeling fades with familiarity. If anything, it deepens. The establishment was not immediately delighted. The two most powerful mathematicians in France at the time, Pierre-Simon Laplace and Joseph-Louis Lagrange, both had reservations and both had the institutional authority to act on them. Lagrange was born in 1736 inches, Turin, by this point in his late 60s, a mathematician of such refinement that he had reformulated all of classical mechanics without a single geometric diagram, pure algebra, pure analysis, impossibly austere. He looked at Fourier's claim and said, essentially, not so fast. His technical worry was whether functions with genuine hard jumps could truly be represented by sums of smooth waves. It was not an unreasonable concern. Laplace was more cautiously skeptical. Together, they delayed Fourier's publication for years. Fourier submitted his memoir to the French Academy in 1807. It sought, he revised and resubmitted in 1811, won a prize, and still the memoir wasn't published. Fourier was certain he was right. He had the calculations. He had the physical intuition. He knew what the mathematics was doing, even when he couldn't yet satisfy every objection. he was essentially correct. The full rigor, the precise conditions under which Fourier's series converge, and to what would take another century to establish completely, but the core claim turned out to be true in a scope even Fourier probably didn't fully anticipate. His memoir was finally published in 1,822 inches, his book on the analytical theory of heat. And here's the connection I keep coming back to, because it still stops me when I think about it clearly. The mathematics Fourier invented to describe heat moving through a metal rod in Napoleonic France is the same mathematics your phone uses to compress a photograph right now. A compression algorithm analyzes any image using a two-dimensional version of Fourier's decomposition, identifying which frequencies of variation are most important, keeping those, discarding the rest. MRI machines reconstruct images of the inside of your body using Fourier transforms directly. The machine collects data in frequency space, and the transform bridges that data into the spatial picture you see on a screen. Audio processing, noise cancellation, the clarity of a phone call, all of it is Fourier's idea, running in hardware that didn't exist until nearly 2 centuries after he first wrote the heat equation down. He was thinking about iron in a furnace. We are using it to see inside brains. And before we move forward, there is a thread that runs backward from Fourier, centuries before him, thousands of miles to the east, Madhava of Sangamagrama, born around 1,340 inches, what is now Kerala in southern India, was doing something structurally related in the 14th century. His school expressed sine and cosine as infinite sums of simpler polynomial terms, decomposing one kind of mathematical object into an infinite assembly of another kind. Fourier's idea is different in its specifics, but the same in its underlying spirit. Complicated things can be built exactly from infinitely many simple repeating pieces. The idea was alive in Kerala 4 centuries before Fourier wrote the word, not transmitted, as far as anyone can determine, independently rediscovered. 2 minds, 2 civilizations, 400 years apart, reaching the same river from different banks. Now, Laplace and Lagrange are more than foils in this story. Their own contributions belong here. Laplace spent his career applying differential equations to celestial mechanics, the motions of planets and moons, the long-term stability of the solar system. The equation that carries his name describes how quantities like gravitational potential are distributed through empty space. Every antenna, every magnet, every electrical circuit exists in a region where the surrounding field obeys the Laplace equation. The equation is invisible. It is everywhere. Lagrange's contribution was stranger and, philosophically, even more striking. He found a completely different way to derive the differential equations of mechanics, not by tracking forces at each instant, but by considering the totality of a motion at once. The principle of least action says that nature, when choosing how a system evolves, always takes the path that minimizes a specific accumulated quantity, a combination of kinetic and potential energy integrated over time. A ball rolling across a surface doesn't just obey local forces moment by moment. In Lagrange's framework, it is somehow selecting the globally most economical path from among all possible trajectories. Nature is precise and nature is frugal, and those two properties turn out to be the same property, expressed as a differential equation. Let that be where it lands for a moment. The Lagrangian framework, incidentally, turned out to reach far beyond classical mechanics. Quantum field theory, the standard model of particle physics, the equations describing how quarks interact inside a proton, all of them are built on the principle of least action. Lagrange wrote it down in 1788 with planets and pendulums in mind, and now here is the pivot. The moment I think about most when I try to explain why this era matters, differential equations stopped being a tool that physicists use to describe the laws of nature. They became the laws themselves, not a notation for the laws. The laws, every principle of classical physics, Newton's equations of motion, the heat equation, the Laplace equation, the equations of fluid mechanics, and Maxwell's equations for electricity and magnetism that followed in the 1860s, every single one is a differential equation from the ground up, not a fact about the world that you then express in differential calculus. A relationship between rates of change, stated completely, with nothing more primitive hiding underneath. What the universe fundamentally tracks is not states. It tracks transitions between states, not where things are, but how they're shifting, not what the temperature is, but how the temperature is curving from point to point. The deepest vocabulary of physical law is the vocabulary of rates and changes the vocabulary of differential calculus, spoken at every scale, from the orbits of planets to the spread of heat through a bar of iron. There's something quietly remarkable about that. The universe is written in the grammar of becoming rather than the grammar of being. For most of the 19th century, this realization produced a very particular kind of confidence. If the universe speaks in differential equations, and if differential equations can, in principle, be solved, then, given the precise current state of any system, you could predict its entire future. The equations carry you forward through time. Laplace said exactly this. Imagine a vast intelligence that knew the position and velocity of every particle in the universe at a single instant. For such a mind, nothing would be uncertain. The entire future and the entire past would lie open, unrolled like a scroll. The clockwork universe, the differential equation as the master key, that was the dream. It was built on 100 years of extraordinary success, and it was reasonable to hold. And for about a century after Fourier and Laplace and Lagrange, the greatest mathematical minds alive worked on more equations, solved them, applied them, and did not know that there was a crack forming in the foundation, not a flaw in the equations, something much stranger, the discovery that even the simplest, most well-behaved differential equations could produce behavior that was, in a deep and precise mathematical sense, permanently unpredictable, not because of missing information, not because the measurements weren't careful enough, because that is what the mathematics genuinely says. The man who found this wasn't looking for it. He was working on a prize problem about whether the solar system is stable, a question Laplace had thought essentially settled. He followed a calculation that seemed, for most of its length, to be going normally, and then he noticed something that didn't belong. A tiny difference in starting conditions was producing a large and growing difference in the trajectory, not an error, not an artifact. The actual behavior of the equations sitting in plain sight. We now call what he discovered chaos, and the man who stumbled onto it, while trying to confirm the elegant predictability of the solar system, was Henri Poincaré. Poincaré had been doing important work for years before he came to that particular problem. He was one of those rare minds who ranged freely across all of mathematics, topology, celestial mechanics, number theory, physics, leaving significant results behind wherever he landed. But let me hold his story for a moment, because to understand what he found, you first need to understand what he was walking into. And what he was walking into was a world that believed, with genuine intellectual confidence, that the future was readable. This was not vague optimism. This was a precise scientific claim, and the man who stated it most starkly was Pierre-Simon Laplace. Working in Paris in the early 19th century, Laplace had watched Newton's equations predict planetary orbits with staggering accuracy. He had watched differential equations model heat, fluid flow, the arc of cannonballs, the oscillation of springs, and he arrived at a conclusion that felt almost inevitable given everything he had seen. Imagine a being, an intelligence, who knew the exact position and velocity of every single particle in the universe at one moment, and who knew all the forces acting between them. What could that being do? Everything, Laplace said. Compute the entire future. Not approximately, exactly. Every planet, every heartbeat, every cloud, every thought, every word anyone would ever speak, all of it already written in the equations. The universe was a machine, a perfect, frictionless, deterministic machine. And the language of that machine was differential equations. We call this imagined being Laplace's demon, not because it's sinister, exactly, but because the implication is a little unsettling once you sit with it. If everything is determined by initial conditions run through physical laws, the future is already fixed, and free will is a useful fiction. We can't predict it only because we're not omniscient, not because anything is genuinely open. In 1814, when Laplace wrote this down, most of the mathematical world thought the demon was right in principle. The universe was computable, deterministic all the way down. But believing determinism and proving it are different things. This is where Augustin Louis Cauchy enters. Born in Paris in 1789, the year the revolution began, Cauchy lived until 1857 and published nearly 800 mathematical papers across his career. He was brilliant and genuinely difficult, deeply royalist in a country moving on from that era, devoutly Catholic in ways that made colleagues uncomfortable, and known to treat his own research as the natural priority over collaborative obligations, admired and exhausting in roughly equal measure. What Cauchy and later Rudolf Lipschitz were working on was a question that sounds almost too basic to need answering. Before you solve a differential equation, you should establish two things. First, does a solution even exist? Second, is it unique? Is there exactly one? Or might there be many solutions from the same starting point? The existence and uniqueness theorems settle both at once. Here's the analogy that makes them feel right. Imagine you're at a crossroads and the sign says, walk in the direction the wind is blowing. Steady wind from the north, clear path, you go south. No wind at all, useless sign. No path exists. Wind swirling in unpredictable eddies, you might start south, veer east, loop back, and someone just 1 millimeter to your left, following the exact same rule, might end up somewhere completely different. The Cauchy-Lipschitz theorem tells you exactly when the sign gives you one clear road. It tells you when the system's rules are smooth enough that from any starting point, exactly one trajectory runs forward. This was the theoretical bedrock Laplace's demon required. If the laws of physics are smooth and well behaved, and 19th century physics offered mounting evidence that they were, then every particle has exactly one future, uniquely determined by its present state. Existence guaranteed, uniqueness guaranteed, demon fully operational. So far, so good. But then there was the three-body problem. Two bodies pulling on each other with gravity have a clean, closed-form solution. Newton worked it out. You write a formula, plug in the starting positions and velocities, and get exact values for where each body will be at any future moment. Beautiful, complete. Three bodies is different, not harder, the way a longer calculation is harder, different in kind. When three objects all pull on each other gravitationally, the resulting system of differential equations cannot, in general, be solved with a neat formula, not because mathematicians haven't been clever enough, not because the right technique is still undiscovered. It cannot be done. In a deep mathematical sense, the equations are perfectly deterministic. There's no randomness in them, but a general closed-form solution simply doesn't exist. This should have been a warning. The solar system has 8 planets, hundreds of moons, millions of asteroids. If the three-body problem resists exact solution, what did that say about whether the solar system was genuinely stable? That question brought us to 1887, to Henri Poincaré, and to one of the stranger episodes in the history of mathematics. For his 60th birthday, King Oscar II of Sweden announced a mathematical prize competition. The most prestigious challenge asked whether the solar system could be proven stable, essentially, a generalized version of the n-body gravitational problem. Poincaré was 33 at the time, born in 1854 inches, Nancy, in northeastern France, already doing work that made colleagues speak of him with cautious awe, possibly the last person alive, some said only slightly as a joke, who understood all of mathematics. He entered with a deep analysis of the restricted three-body problem and the simplified version, where one body is too small to gravitationally affect the other two. he developed new geometric methods for studying differential equations, methods that hadn't been tried before. The judges, including the great analyst Karl Weierstrass, were impressed. Poincaré won the prize. The paper went to the printer. Then one of the editors, reviewing it, found a problem, not a typo, a conceptual gap, a place where Poincaré had assumed something without proving it, and where the assumption turned out to be wrong. The editor wrote privately. Poincaré looked at the correction, and the ground shifted. When he tried to repair the argument, when he did the analysis properly, without the unjustified assumption, what he found was not a corrected version of the original claim. What he found was its opposite. The paper had to be recalled. Poincaré paid for the recall out of his own funds, at a cost that exceeded the prize he had won. He went back to work, and what emerged from that forced return was something nobody had been looking for. He found orbits that didn't repeat. Instead of planets returning to their starting positions and looping around in tidy periodic paths, Poincaré found trajectories that wandered, that came close to repeating but never quite did. And he found that for certain configurations, the long-term behavior of the system was extraordinarily sensitive to how it started. Not sensitive in a way that more careful measurement could fix. Sensitive in a way that no improvement in measurement could ever correct. Picture two identical twins starting a walk from spots exactly 1 millimeter apart. They follow the same instructions, step by step, with perfect precision. After 1,000 steps, one is in Paris, the other is in Tokyo. That is not an exaggeration for effect. That is what the mathematics says. Shift the starting position by an amount smaller than anything you could ever measure, and the long-term trajectory changes completely. This is sensitivity to initial conditions. This is the mathematical heart of chaos. And here's what it does to Laplace's demon. The demon needed not just the right equations, differential equations, provided those. The demon also needed perfect knowledge of every starting position and velocity. But if even an infinitesimal uncertainty in that knowledge grows over time, without bound, then perfect prediction isn't a question of being careful enough. It's impossible in principle. And here is something that deserves a moment of quiet recognition. These equations describing planetary orbits, river flow, a beating heart are perfectly deterministic. No randomness in them, no coin flip, no hidden uncertainty. And yet they produce behavior that is, for all practical purposes, permanently unpredictable. The chaos is not a flaw in the physics. The chaos is written into the mathematics itself. Determinism and unpredictability coexisting perfectly in the same equations. Let that settle for a moment. Poincaré found this while trying to fix an embarrassing error in a prize-winning paper. The wrong version of the argument opened a door. The right version would have walked past. I think about that sometimes. The error was not a failure. It was a portal. Now, before we follow this thread further, let me tell you about someone working at almost exactly the same time, in the same broad territory, under considerably more obstructed circumstances, Her name was Sofia Kovalevskaya. Born in Moscow in 1850, her father was a military officer, and from a young age, she showed a consuming interest in mathematics, which was a problem. Because in Russia in the 1860s, women were legally prohibited from attending university. Here is how she solved that. She married a man named Vladimir Kovalevsky, a paleontologist, in what both understood from the start to be a formal fiction. The marriage was a legal instrument. It gave Sofia the right to travel abroad independently of her father's authority. Vladimir was fully aware of what the arrangement was. They were fond of each other in a complicated way, but the marriage existed primarily to get Sofia onto a train to Germany. In Berlin, she sought out Karl Weierstrass, yes, the same Weierstrass on the prize committee that later judged Poincaré's submission. Women were not admitted to the University of Berlin. Weierstrass agreed to see her privately, probably as a courtesy, and set her a collection of problems he normally used to assess his best doctoral students. She came back with the solutions. Weierstrass wrote afterward that he had never encountered this quality of mathematical thinking in a student of any kind. He became her strongest advocate. In 1874, she earned a doctorate from the University of Göttingen in absentia. She still couldn't attend in person, becoming the first woman in history to hold a doctoral degree in mathematics. She proved the Cauchy-Kovalevskaya theorem. A central existence result in partial differential equations. She won the Prix Bourdin from the French Academy of Sciences in 1888 for work on rotating bodies that so exceeded expectations. The judges increased the prize money mid-deliberation because the standard amount felt inadequate. She became a professor at Stockholm University, one of the first women in Europe to hold a full academic chair in mathematics. She died in 1891 at 41 of pneumonia. There's something that gets me about the way these lives intersected. Weierstrass, who tutored Kovalevskaya privately because the university wouldn't let her in, sat on the same prize committee that recognized Poincaré. Her existence theorems and his chaos work were pressing at the same enormous question from different angles. What do differential equations actually do over time? And when can we trust their answers? No. Let me draw the line from Poincaré's discovery to the world you actually live in. In the 1890s, chaos was a mathematical curiosity, profound, undeniable, deeply strange, but abstract. Whether three celestial bodies could behave chaotically mattered to mathematicians. It wasn't obvious it affected anyone else. Then, in the 1960s, a meteorologist named Edward Lorenz was running weather simulations on an early computer at MIT. He wanted to recheck a simulation by restarting it from the middle of a previous run. Instead of pulling the initial conditions from the machine's stored memory, he typed them in from a printed readout, rounding to 3 decimal places instead of the full 6 the computer held internally. He started the run and went to get coffee. He came back to find that the weather pattern that emerged was completely unrecognizable, entirely different, all from a change in the 4th decimal place. Lorenz hadn't found a bug. He had rediscovered Poincaré's result 70 years later on a completely different problem. And here's what's genuinely wild. The atmosphere is a chaotic system described by differential equations. The equations governing fluid motion, temperature, pressure are well known. They're not mysterious or incomplete, and Poincaré's mathematics lives inside them. Sensitivity to initial conditions in those equations means that a tiny uncertainty in today's atmospheric state grows large enough to overwhelm any forecast in roughly 10 days. Not because computers aren't fast enough, not because models aren't sophisticated enough. 10 days is approximately the mathematical horizon for weather prediction, written into the structure of the equations themselves. This is why your 7-day forecast is reasonably reliable and your 14-day forecast is essentially a sophisticated guess. Poincaré found the mechanism in the 1890s, studying free gravitating bodies. Lorentz rediscovered it in the 1960s, studying the atmosphere. Same mathematics, completely different settings. One of those connections across time that shows you how deep the differential equation thread runs. Laplace's demon isn't wrong. Exactly. The equations are still deterministic. Cauchy and Lipschitz weren't mistaken. For any perfectly known starting point, exactly one trajectory runs forward. The demon's logic is airtight. The demon's problem is that a perfectly known starting point doesn't exist in practice and in chaotic systems. The gap between perfectly known and very precisely known is infinite. The universe is not playing dice. The equations are exact, and they tell you that some futures are simply beyond the reach of prediction, not because of missing information, but because of how the mathematics itself behaves. That is what Poincaré found while fixing a mistake, while competing for a birthday prize from a Swedish king. But the 20th century was about to discover something even stranger. Differential equations weren't just describing the world of planets and bridges and heat. They were about to describe a world where particles exist in two places at once, where observation changes reality, and where the equation itself is the most fundamental thing that exists. So here we are, the 20th century, and if the story of differential equations had ended with Newton and Laplace and Poincaré with gravity and heat and orbits and chaos, it would already be one of the great intellectual adventures in human history. But it didn't end there, not even close, because between roughly 1900 and 1960, differential equations stopped being a tool that physicists used to describe the world. They became the world, or at least they became the most fundamental language we have for describing everything the world is made of. And I don't mean that loosely. I mean it almost literally. Let me start with one of the most extraordinary scenes in the history of science. It is December of 1925, and a 38-year-old physicist from Vienna named Erwin Schrödinger has just escaped to a mountain resort in the Swiss Alps with a woman who was not his wife. Schrödinger was brilliant, charming, reckless, and apparently very productive under romantic pressure, because over the next 2 weeks, while skiing and otherwise enjoying his holiday, he wrote down an equation that changed everything we know about reality. That equation is called the Schrödinger equation, and it is a differential equation. Now, before I tell you what it describes, let me give you a picture. Imagine a weather forecast for a single electron not for tomorrow's rain, but for the probability of where an electron might be found and how that probability shifts and flows over time. The Schrödinger equation does exactly that. It doesn't tell you where the electron is. What it tells you is the probability of where the electron might be, expressed as something called a wave function. And that wave function evolves forward in time according to a differential equation. The electron's possible futures are guided by this equation, the way a river is guided by the shape of the ground beneath it. And here's the thing that makes this genuinely strange. The wave function isn't just a stand-in for our ignorance. The electron doesn't have a definite position until someone measures it. Before measurement, it inhabits multiple possibilities simultaneously, and those possibilities are described by a solution to a differential equation. The entire microscopic world, every atom, every molecule, every chemical bond, every semiconductor in the device you're listening to this on follows from this one equation that a romantic escapee wrote in the Swiss Alps in December of 1925. I find that genuinely astonishing every time I think about it. Now let's move one level bigger. Not electron, but space-time itself. In 1915, Albert Einstein, born in Ulm in 1879, raised in Munich, a man who spent years working as a patent clerk after failing to get an academic post after graduation, published a set of equations that redefined our understanding of gravity and the structure of the universe. Einstein's field equations are coupled, nonlinear partial differential equations. And if that sounds like a mouthful, here's the intuitive picture. Think of them as a conversation between space and matter. Matter speaks first and says, I'm here, I have mass, I have energy. Space-time listens and says, fine, I'll curve around you. And then the curvature speaks to everything else and says, move along these paths. That entire conversation, matter, telling space-time how to curve. Curved space-time telling matter how to move that back and forth is a differential equation. The most beautiful one, many physicists would say, ever written. What falls out of Einstein's equations is extraordinary. Black holes, gravitational waves, ripples in the fabric of space-time itself, which we detected for the first time in 2015, when two black holes, a billion light years away, spiraled into each other and sent a tremor through reality so faint it shifted mirrors by a fraction of a proton's width. The Big Bang, the expansion of the universe, all of it. Solutions to a system of differential equations that Einstein wrote while working in Bern, which is a sentence I will never quite get over. Let's add another layer. About 50 years before Einstein, a Scottish physicist named James Clerk Maxwell sat down and wrote four differential equations that describe everything electromagnetism can do. The way electric fields form around charges, the way magnetic fields curl around moving currents, the way a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, each one forever generating the other. And here's what Maxwell noticed when he looked at all four equations together. A solution popped out that key, an oscillating disturbance that moved through space at a speed that fell out of the equations themselves, a speed that turned out to be exactly the speed of light. Maxwell hadn't been looking for light. He'd been studying electricity and magnetism, but light fell out of his equations like a secret the universe had been keeping. Light is a solution to Maxwell's equations, and Maxwell's equations are four differential equations, which means, if you sit with that for just a second, that the light you see by the light bouncing off everything around you right now is a differential equation made visible. By the early 20th century, the world around us was filling up with things built on differential equations. The wings of aircraft designed using equations for airflow, the cables of suspension bridges shaped by equations balancing tension and gravity, the circuits in every electronic device governed by equations describing how current and voltage change over time. The modern engineering world is, in a sense, a differential equations machine made physical. And then things get more interesting still, because differential equations didn't stop at physics and engineering. They moved into biology. In 1952, and this is one of my favorite chapters in this whole story, two British physiologists at Cambridge, named Alan Hodgkin and Andrew Huxley, published a mathematical model of how a neuron fires. A neuron transmits its signal electrically, a voltage pulse called an action potential that travels down the cell like a wave. What Hodgkin and Huxley did was probe giant nerve fibers from squid big enough to measure experimentally, which is an image I enjoy, and then write down four coupled differential equations describing how the voltage across the cell membrane changes as ion channels open and close. When they solved those equations numerically, by hand calculations that took weeks, the solutions reproduced the exact shape of an action potential. Not approximately, exactly. They won the Nobel Prize in 1963. Their model is still used today in computational neuroscience and in early-stage neural implant design. The mathematical foundation underneath everything we understand about how your brain generates a thought is a set of differential equations written by two men probing squid nerves in Cambridge. The neurons firing in your brain right now are following differential equations. Let that sit for just a moment. Around the same era, differential equations were quietly colonizing ecology. In the 1920s, an Italian mathematician named Vito Volterra and an American chemist named Alfred Lotka independently wrote down equations to describe predators and prey. Picture rabbits and foxes. When rabbits are plentiful, foxes thrive. When foxes grow numerous, rabbit populations fall. When rabbits grow scarce, foxes starve and decline. When foxes decline, rabbits recover, and round and round. The Lotka-Volterra equations captured this as a pair of differential equations. And what they reveal is that the populations don't crash, they cycle endlessly, a slow oscillation encoded in mathematics. The same structure underlies the SIR model of disease spread, susceptible, infected, recovered, three groups, three differential equations. Every epidemiological model used to forecast the course of an epidemic, including the ones that shaped public health decisions in very recent memory, traces its mathematical ancestry to this framework. And then, in the 1970s, differential equations walked into finance. This is the part of the story that I think is genuinely underappreciated. and also a little eerie. Three economists, Fisher Black, Myron Scholes, and Robert Merton, were trying to figure out how to correctly price a financial option, a contract giving you the right to buy a stock at a fixed price in the future. It's a question about uncertainty, about the price of risk over time. The mathematics they developed connects to something unexpected. Think of a metal bar, hot at one end and cool at the other. The heat diffuses through the bar over time, spreading from hot toward cool, smoothing out. The mathematics of that process is a differential equation, the heat equation, one of the great classical equations of physics. And it turns out the mathematics of pricing a stock option is structurally identical to the mathematics of heat diffusing through metal, the Black-Scholes equation, which earned Scholes and Merton the Nobel Prize in Economics in 1997. Fisher Black had died by then, is a partial differential equation describing how an option's value changes as time passes and as the stock price moves. This is either deeply beautiful or deeply unsettling, depending on your perspective. The same mathematical machinery that describes a cooling bar is the machinery Wall Street used to price trillions of dollars of financial instruments. And when that machinery was applied incorrectly, when its assumptions about market behavior broke down during extreme events, it contributed to the fragility behind the financial crisis of 2008. A differential equation from thermodynamics, repurposed for finance, whose failure modes helped destabilize the global economy. That's not a metaphor. That's what happened. Now, here's where I want you to do something a little unusual. Take a slow breath and hold everything we've covered in this part in your mind at once. The equation that tells an electron where it might be, the equation that tells space-time how to curve, the equation that tells light how to propagate, the equation that tells a bridge how much weight it can hold, the equation that tells a neuron when to fire, the equation that tells a population of rabbits and foxes how to cycle, the equation that tells a disease how to spread, the equation that tells a financial derivative what it's worth. They're all differential equations. Not the same equation, completely different equations, describing completely different phenomena developed in completely different fields by people who were often not thinking about any of the others at all. But the same kind of thing, the same fundamental structure, a rule about how something changes and what that change depends on. The universe doesn't seem to store answers. It stores rules about how things change. And those rules are differential equations, which means everything, the precision of physics, the utility of engineering, the accuracy of biology and epidemiology and finance rests on one idea. The idea that the relationship between a quantity and how it changes is the deepest fact you can know about it, not what something is, how it changes, and that, I think, is the most quietly profound thing mathematics has uncovered about the structure of reality. There's a mathematician worth pausing on here, someone whose work sits quietly underneath a lot of what I've been describing Xing Chen was born in Jiaxing, China in 1911. He came of age during a period of enormous political upheaval, war, revolution, the mid-20th century transformation of China. He ended up at Princeton, then Berkeley, and became one of the central figures in differential geometry, the field that asks what geometry looks like in curved spaces. Chern's work provided mathematical tools that modern physics genuinely needs, the geometry that Einstein's equations live in, the deep structure of gauge theories in quantum field physics. Chern's fingerprints are there. He died in 2004 at 93, still mathematically active. There is something I find quietly moving about that. Now, let me tell you something about how any of this actually works in practice. Because most of the differential equations I've been describing cannot be solved by hand. Not Schrödinger's equation in any real physical situation. Not Einstein's equations for anything more complex than a single spherical mass. Not the Navier-Stokes equations for fluid flow in general. The equations exist. The equations are exact. But finding a closed form solution in the full complexity of a real situation is usually impossible. So we approximate. Computers take the equations and divide space and time into tiny grids, stepping from point to point, calculating as they go. This is called numerical methods, and it is an entire scientific field. The Ranjakuta methods, developed in the early 20th century, are among the most widely used algorithms in all of computing. Numerical recipes for stepping through a differential equation, one tiny increment at a time. Finite element methods break a physical object into millions of tiny pieces and solve the equations across each one. Every weather forecast, every climate simulation, every aerodynamic analysis of an aircraft wing, all of it is computers numerically solving differential equations, step by step, billions of times per second. The equations that can't be solved by hand are solved instead by the sheer arithmetic force of machines. And the results are, to a degree that should probably astonish us more than it does, correct. And there are equations that have been sitting in front of us for 2 centuries that we still can't solve, haven't solved yet, can't at least, not with anything we currently know. The Navier-Stokes equations are still one of the great unsolved problems in mathematics. A $1 million prize from the Clay Mathematics Institute awaits whoever proves whether smooth solutions always exist. We can simulate fluid dynamics on computers with extraordinary accuracy, but a complete mathematical proof still out of reach. There are places where the equations break down, places where the mathematics itself seems to stop speaking clearly. And those silences at the edge of what we can solve, those are where we're going next. So let's go there, to the silences. There is an equation, 2 equations, technically, though they work together so closely that almost everyone just says them as one, that sit at the center of one of the strangest situations in all of mathematics. The equations are called the Navier-Stokes equations, and they describe the motion of fluids, water flowing around a rock, air curling over the wing of a plane, blood pushing through the chambers of a heart. Claude Louis Navier Was born in Paris in 1785, a child of the revolution, trained as an engineer in the tradition of the great French technical schools that believed mathematics was built to be used. He wrote the equations in 1822. George Gabriel Stokes came a generation later, born in 1819 Inches, a county Sligo, on the western coast of Ireland, the youngest of 8 children of a country rector, and by most accounts, one of the most meticulous mathematical physicists of the 19th century. He refined the equations and put them on firmer theoretical footing in 1845. Between them, working across different decades and different countries, they gave us a mathematical description of fluid motion that has lasted 200 years. And here's the thing, those equations work not in a restricted, idealized, special cases way. They work the way engineers mean when they say something works. You can stake lives on them. Every commercial aircraft that flies uses them. Every submarine that navigates, every weather simulation running on a supercomputer. The equations have never been demonstrably wrong in any practical application, and yet nobody has been able to prove that they always behave. What does that mean? Always behave? Imagine you start the equations running with a smooth, gentle flow, calm water, barely stirring. The question is, does the mathematics remain well behaved as you evolve that flow forward in time? Or could the equations, under some specific conditions, develop a singularity, a point where the velocity shoots off toward infinity, a place where the mathematics itself stops making sense? In 2 dimensions, this question has been answered. 2-dimensional fluids, mathematically speaking, always stay smooth. But in 3 dimensions, which is the actual world, the answer is unknown. Nobody has proved singularities can't form, and nobody has proved that they can. The question just hangs there. The Navier-Stokes problem is a bit like having a recipe that always produces perfect bread in your kitchen, every single time, for 200 years. But you cannot prove that the recipe won't. At some point, under some conditions nobody has tried yet, produce bread that expands to fill the entire universe. The recipe works. The proof that it always works doesn't exist. And I've always found that gap between the practical and the provable quietly extraordinary. The Clay Mathematics Institute included Navier-Stokes on their list of 7 Millennium Prize problems in the year 2000. $1 million waits for whoever resolves it. As of right now, the prize is unclaimed. I find this almost philosophically vertiginous. We have been living with these equations for 2 centuries. We use them to build the modern world, and we still cannot confirm, in the deepest mathematical sense, whether they are always describing something coherent. Terence Tao has come the closest to understanding this problem that any living mathematician has come. Tao was born in Adelaide, Australia, in 1975, won the Fields Medal in 2006, learned to read at roughly the age of 2, and was working on university-level mathematics by the time he was 8. He is, without much controversy, one of those mathematicians who makes other exceptional mathematicians quietly feel they are playing a different sport. In recent years, Tao proved that certain modified versions of the Navier-Stokes equations can produce solutions that blow up in finite time. This does not mean the real equations blow up. The modifications matter enormously, but the result tells us that any proof of the real equations staying smooth will need to be very precise about what makes them different. Whatever it is that protects fluid dynamics from mathematical catastrophe, it is something specific, something delicate, and we haven't yet named it clearly enough to write a proof around it. Which, I mean, think about what that implies. We rely on these equations every single day, in every plane and every forecast. And the thing that makes them safe, in the mathematical sense, is still unnamed. Now, let me take you somewhere that feels, at first glance, like a completely different world. In 2018, two researchers at the University of Toronto named Ricky Chen and David Duveneau published a paper that introduced something called neural ordinary differential equations. The central idea was almost disarmingly simple. Traditional neural networks, the kind that power the AI systems reshaping the world, are built in layers. Information goes in, passes through layer 1, layer 2, layer 3, each layer transforming it in some learned way until an answer comes out. The layers are discrete. It's a staircase. Each step is its own separate thing. Chen and Duveneau asked, what if those steps became a smooth, continuous flow? A neural ODE is like replacing the staircase with a ramp. The same distance gets covered, but instead of distinct steps, you have a slope described at every point by a differential equation. Instead of discrete layers, a continuous rule about how the representation of the data changes as it moves through the network. This turns out to matter in practical ways. Networks described this way use memory more efficiently. They handle time series data more naturally, and they connect the whole project of modern machine learning to something 300 years old. The training process itself, the process by which a network learns from its errors, is in the continuous limit, a differential equation, gradient descent, the algorithm underneath almost all of deep learning, is at its mathematical core a rule about how quantities change in response to other quantities, which is to say, a differential equation. There's something about this I genuinely love. These AI systems that feel impossibly modern, these things that can write and reason and generate, are running at their mathematical bedrock on concepts that Newton and Leibniz would recognize immediately: the chain rule, the derivative, the differential equation as the natural language for describing how something changes, still there, still doing the work 300 years later. And here is where differential equations become not just intellectually interesting, but urgently, undeniably real. Every weather forecast you have ever checked is a numerical solution to differential equations, not as a metaphor. The actual computation that produced that percentage chance of rain on your phone was an approximation to a system of coupled nonlinear partial differential equations describing the state of the atmosphere. The atmosphere is a fluid. It obeys equations in the same family that Navier and Stokes wrote. Every climate model, every projection of how global temperatures evolve as carbon dioxide rises, every estimate of sea level and storm frequency is differential equations solved approximately on supercomputers. Billions of arithmetic steps approximating continuous flow and the fundamental limit on how accurate a weather forecast can be. The reason you can predict tomorrow with confidence, but not next month with any confidence at all, is the chaotic sensitivity Poincaré discovered in the 1880s. Small errors in the initial conditions grow exponentially in a nonlinear system. The butterfly effect is not a metaphor. It is a property of these specific equations. When climate scientists express uncertainty, when they give ranges rather than single numbers, that epistemic humility is baked directly into the structure of the mathematics. The equations tell us what is knowable, and they tell us exactly where knowability runs out. That is one of the most honest things about differential equations. I think they don't just describe the world, they also describe the limits of our ability to describe it. And here is maybe the deepest thing, the thing that keeps surfacing the longer you sit with any of this. The laws of physics are differential equations, every single one. Newton's second law is a differential equation, acceleration being the rate of change of velocity. Velocity, the rate of change of position. Maxwell's equations for electricity and magnetism are differential equations. Schrödinger's equation, which governs quantum particles, is a differential equation. Einstein's field equations, which describe how mass curves spacetime, are differential equations. Every foundational law we have found about how the universe operates is a statement about rates of change, not about where things are, about how things are changing. Let that sit for a moment. The universe does not seem to store information about where things are. It stores information about how things change. A differential equation doesn't say the temperature here is 50 degrees. It says the temperature here is changing at a rate proportional to the difference between itself and its surroundings. The rule is the reality. The state is just a consequence. And I think this is one of the most genuinely surprising things humanity has discovered, that the deepest language the universe speaks is not a language about place or quantity, but about change, pure and continuous and unceasing. This is an extraordinary philosophical claim. It means the fundamental currency of the universe, the thing the deepest laws are written in, is not position or quantity or even energy in some static sense. It is change, instantaneous, continuous, moment by moment change. The universe is not a collection of snapshots. It is a set of rules about motion, forever in the middle of being applied. And here is what makes these equations genuinely hard. When they are hard, we are creatures of finite time trying to hold infinity in our hands. Differential equations describe continuous change at every instant, in every part of space, forever. When we solve them exactly, we are somehow reaching all of that infinity at once, and compressing it into a clean answer. When they resist being solved exactly, it is because the infinity is too tangled, too woven through itself to be unraveled in one stroke. Navier-Stokes is hard because three-dimensional fluid flow can develop structures so intricate that the infinity refuses to compress. The equations are not wrong. They are just enormously, patiently more complicated than we are. That is not a failure. That is mathematics being honest about the world. We have come a long way, you and I want to spend a few moments just looking back at the road. We started with clay tablets, Babylonian astronomers pressing their observations of Jupiter into wet clay, tracking not where the planet was, but how fast it was moving and how that speed was changing. That was already, in its essential structure, the beginning of all of this. The idea that what matters is the rate, the motion, the change itself. We watched Archimedes in Syracuse around 250 years before the Common Era, chasing curves with triangles, filling gaps with smaller and smaller shapes, getting closer and closer to something exact without ever quite touching it. A method that was always, it turns out, going to lead somewhere enormous. We kept company with the Bernoulli family across decades of brilliant, occasionally uncharitable competition. Jacob and Johann arguing in published papers, and in the middle of all that turbulence, producing mathematics of lasting beauty, the shape of the hanging chain, the path of fastest descent, the early foundations of what became the calculus of variations. We followed Leonhard Euler, who worked with such relentless focus that he lost the sight in one eye and kept going, then lost the other and kept going still, producing mathematics by dictation in a darkened room, filling more pages than almost any person who ever lived. We stood with Joseph Fourier as he tried to understand heat spreading through a metal bar and discovered, unexpectedly, that any function at all can be decomposed into waves, sine and cosine layered on top of each other, their frequencies adding and canceling, reconstructing the original from pure oscillation. He used a differential equation to find this. The solution led somewhere deeper than the question. We watched Henri Poincaré follow the mathematics of three orbiting bodies honestly wherever it led, and accidentally discover chaos, that determinism and predictability are not the same thing, that a system can be fully governed by exact rules and still refuse, in practice, to tell you what comes next. We spent a December with Erwin Schrödinger in a ski chalet in the Austrian Alps, arriving with a mysterious companion and emerging 2 weeks later with a differential equation describing the quantum world more accurately than anything before it. The equation still sitting at the center of chemistry and physics and everything built from the behavior of atoms. And now we have arrived here at Navier-Stokes waiting with its $1 million silence. And at neural ODEs, discovering that the mathematics of continuous change lives inside artificial intelligence. And at the climate supercomputers running the atmosphere's equations forward in time, doing their best, honest about where the certainty ends. One long thread, from the Babylonian tablet to the neural network, from the polygon pressed into the parabola to the ramp that replaced the staircase. Still unspooling, the universe speaks in differential equations, not because someone decided it would, not because they are particularly elegant, though they often are, but because the universe, as best we can tell, is a place made of processes rather than states, made of change rather than things. The laws don't describe a frozen picture. They describe a flow, an ongoing, continuous, never finished unfolding. Every generation has added a little to our ability to listen. The Babylonians heard the motion of planets and tried to write it down. Archimedes heard the shape of curves and tried to measure them. Newton and Leibniz found a language precise enough to hold instantaneous change. Euler extended that language outward. Fourier heard that heat speaks in waves. Poincaré heard chaos, where others heard order. Schrödinger heard the quantum world, and the listening continues. Somewhere right now, there is a mathematician working late on the Navier-Stokes problem, not because anyone assigned it to them, but because they cannot quite let go of the question, because it has been sitting there for 200 years, and they think, quietly, that perhaps this approach is the one, and somewhere right now, a climate model is running its billions of arithmetic steps, approximating the continuous, trying to give us the best answer the mathematics will allow, honest about the horizon where certainty ends, one thread, thousands of years long, still being woven. You have been with this thread for a long time tonight, and now it is time to let it rest. The equations are still there, passion, as they have always been, in the structure of things. The universe will keep changing, quietly, moment by moment, according to its rules, while you sleep, and the equations will still be there in the morning.